So for this PowerPoint presentation, we're going to have the normal distribution approximating other types of distribution. The normal approximation to a binomial. If a binomial random variable with the parameters n and p, such that the mean is np and the variance would be np times 1 minus p, so we have z is equal to x minus np over square root of np times 1 minus p. It's approximately a standard normal random variable. To approximate a binomial probability with a normal distribution, a continuity correction is applied as follows. So if we want to have the probability of x less than or equal to x, it would be equal to the probability of x less than or equal to x plus 0.5, or approximately equal to the probability of z less than or equal to x plus 0.5 minus np over square root of np times 1 minus p. The approximation is good for np is greater than 5 and np times 1 minus p, np is greater than p and n times 1 minus p greater than 5. So this approximation is good with mean greater than or equal to 5 and its complement also greater than or equal to 5. Now take note of this correction factor. So if we will be assuming a number line, such that we have 1, 2, 3, and 4, for example. So we will be having the boundaries between 1, 2, 3, and 4, such that when you say x is greater than 1, so it would be x greater than or equal to 1.5. But if you say x is greater than or equal to 1, it would be x greater than or equal to 0.5. So we will be including, so the cutoff would be the plus or minus 0.5, and it is up to us to include or not include the given number. Example. In a binomial probability distribution with p is equal to 10 raised to negative 5 and n is equal to 16 times 10 to the 6 times, find the probability that x is less than or equal to 150. So z is equal to x minus np over square root of np times 1 minus p, and then there is a correction for x. So when we say less than or equal to 150, so if this is 150, less than or equal, so it would be 150 is included, so it would be x less than 150.5, less than or equal to 150.5. So that would be 150.5 minus np, n times p, square root of n times p times 1 minus p. And to solve for the probability, it would be 0.227. Suppose that x is a binomial random variable with n is equal to 200 and p is 0.4. So np, so the mean is np, so that's 200 times 0.4 is 80. So the mean is 80, and then the standard deviation is 200 times 0.4 times 0.6. So we get the square root of that, so that's square root of 48. So we are looking for the probability of x less than or equal to 70, the probability of x in between 70 and 90, exclusive, and the probability of x equal to 80. So if this is 70, so this is less than or equal to 70, so we are looking for less than 70, and 70 is included. So we're looking for the probability that x is less than or equal to 70.5. So that's the probability of z less than 70.5 minus 80 over square root of 48. So that is a phi of 70.5 minus 80 divided by square root of 48. So that's negative 1.37. And to solve for that area, it is 0.085344. For the probability of between 70 and 90, but this time it is exclusive. It's not included, so we are not going to include 70, and for 90 we are not going to include 90 as well. So that would be the probability that x is in between, so 70 is not included, so that's 70.5 up to 90.5. So that would be the probability of 70.5 minus 80 divided by square root of 48, and then 90.5 minus 80 over square root of 48. So that would be, for the upper limit, 90.5 minus 80 divided by square root of 48, it would be 1.52 minus phi of negative 1.37. So evaluating this probability, 1.52, and then negative 1.37. So the probability is 0.850396. Now, if we want equal to 80, so that is from 79.5 to 80.5. So the probability that x is in between 79.5 to 80.5 would be equal to the probability that z is less than 80.5 minus 80 over square root of 48 minus the probability of z less than 79.5 minus 80 divided by square root of 48. So this is a phi of 0.07 minus phi of, I think this is negative 0.07. So this would give us 0.0558. Next problem, there were 49.7 million people with some type of long-lasting condition, disability living in the United States in 2000. The probability, or it was represented at 19.3%, so 0.193 of the majority of civilian age 5 and over so a sample of 1,000, so n is 1,000, so the mean is 193. So the standard deviation is the square root of np times 1 minus p, so that's 193 times 0.807. So sigma is 12.48. Approximate the probability that more than 200 persons. So the probability of x greater than 200 have a disability. So if this is 200, more than 200, so that would be the probability of x more than or equal to 200.5. So this is a phi of 200.5 minus 193 over 12.48. So that would be 2.12. So phi of 2.12. (0.983). Next, approximate the probability that between 180 and 300 in the same have disability. So we're looking for the probability of between 180 and 300. So if we're going to include 180, it should be from 179.5 to 300.5. So that would be phi of 300.5 minus 193 over 12.48 minus phi of 179.5 minus 193 over 12.48. So 300.5 minus 193, divide this by 12.48, this is 8.61. So 8.61, and then so for the lower limit, 179.5 minus 193 divided by 12.48, this is negative 1.08. So to solve for the probability, we have 8.61 and then For the upper limit, for the lower limit, it's negative 1.08. So 0.8599. Now we can also approximate the Poisson process. So take note that the mean is lambda and the variance is also lambda. So the formula would now be this one. Z is equal to x minus the mean over the standard deviation. So there is still, since this is still a discrete distribution which is converted into continuous, there is still a correction factor. There is still a correction factor, and this is applicable when sigma is reaching, when lambda is reaching 5. So assume that the normal asbestos particle of a squared meter of dust on a surface follows a Poisson distribution with mean 1000. If a square meter of a dust is analyzed, what is the probability that 950 or fewer are found? So this is 950 and fewer. So it would be less than or equal to 950.5. So that would be 950.5 minus lambda over square root of lambda. So this would be the calculated probability. If you want the actual value, it would be from 0 to 950 of the Poisson distribution. However, the calculation for 0 to 950 is quite tedious, that it's not practical to solve for this one using the exact method, because this is somewhat similar, or this is approximately equal when you're going to calculate this. Okay, so next. Hits to a high volume site are assumed to follow a Poisson distribution with a mean 10,000. Approximate the following: the probability of more than 20,000 hits in a day. So more than, so it's not included, so it would be 20,000, 20,000.5. So we're looking for the probability that x is greater than or equal to 20,000.5 minus 10,000 over the square root of, so this is now the z value, over square root of 1000. So this is greater than, so this is 1 minus phi of 20,000.5 minus 10,000 divided by square root of 10,000. So this is 100.5. I think this is almost 0. So this is 1 minus p of 100.5. So this is approximately equal to 0. Next, probability of less than 9,900 hits in a day. So this is the probability that C is less than or equal to, so less than, so we're not going to include this. So that's 9,899.5 of minus 10,000 over square root of 10,000. So this is less than, so phi. So that's 9,899.5 minus 10,000 divided by square root of 10,000. So this is negative 1. and phi of -1 is 0.15866. Find the value of the probability that the number of hits exceeds a value of 0.01. So the probability that the number of hits in a day exceeds a value is 0.01. So P of z greater than z is equal to 0.01. So the area to the right is 0.01. So this is 1 minus phi of z is 0.01. So phi of z is equal to 0.99. The value of z here, I think, is equal to, let's check whether it is 2.33. So I think it's indeed 2.33. So 2.33 is equal to x minus mu, or x minus lambda over square root of lambda. We know that lambda is 1000. So x minus 1000 over square root of 1000. So 2.33 times square root of 1000 plus 1000 is an x equal to 1073.69. So we're looking for greater than z. So since this is greater than z, so 1073 is the answer. If you will be using 1073, you're going to have some adjustment of 0.5. So greater than 1073 is 1073.5. So let's skip the other problems. So these are some of the problems you can answer relating to that one. And these are some of the summary and the references.